As we've alluded to in the last few videos, a polar equation has a period. But that period for the polar equation is not the same as the period for the rectangular equation. Rectangular equations have periods that are a little bit more set in stone, but the polar equation's not so much. So a polar equation is the smallest interval from 0 to p for the angle theta that's required to view the entire curve, in other words, before it repeats itself. So I like to think of it as a circuit, right? So in other words, you're getting one full circuit to generate one full circuit of the curve. To use calculus with polar equations in particular, we're going to need to be able to find the period. Say if we want to find the integral, perhaps, we're going to need to know the period, because that'll be the limits of integration, per se. So, or one might say, not per se. So the period of the function in Cartesian is not the same. So there are some tricks for learning Cartesian periods. So if it's a sine curve, it's this to this, and if it's a cosine, blah, 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 right? There are formulas for that, but that is not the same as polar. Polar does not work that way. We already saw that, as a matter of fact, with previous graphs in Desmos. So if I went back here, the period for, well, the easier one to see is actually this one. The period for the Cartesian graph is pi, right? So 0 to 2 pi actually has 2 full hills and 2 full troughs, or 2 full valleys. You don't need all of that. So you're actually done with the Cartesian graph at pi, but you are not done with the polar graph at pi. You've only gone through 2 of the petals so far, and you need to go 2 more to make it work. So the Cartesian and polar are not the same. So see the rose curves on page 23. So see example 11 and page 23. Okay. All right. Unfortunately, there is no method. There is no method that's going to get you a polar other than thinking about it using trial and error, so using your brain. But there is no method to find the period of a polar equation. There, you'll sometimes see online, there's like a little trick for like one special kind of curve, but it doesn't always work. So what's the point in that? So you can use logic, you can use trial and error, but let's get real. What you're really going to use is Desmos, or Desmos, depending on how you pronounce it. That's the one, right? We're going to use computers, right? That'll help. All right, so let's look at all 4 of these. So we'll start off with the first one. So r equals 1 plus 2 cosine theta. And now here's the trick that really helps. You're going to need to know how to do, oh, this is the one, how to do what I'm doing. So normally when I graph, let me graph this particular function. So it was r equals, let me see, r equals 1 plus 2 cosine theta. Oop. Sorry, went the wrong way. Plus, there it is, 2 cosine theta. By the way, to do theta, I'm just typing theta. You actually can get it out of the little menu down below as well by messing around in there in the functions and stuff. Okay, so that's all well and good. So you can play around with theta. You can kind of go that way and kind of see, oh, that's not a full graph. That's not good. And you can play around. I'm going to turn off this other graph because we don't need it. So you can do it that way just by trial and error. Just kind of like 3 pi. Oh, I've got a full curve. What about 2 pi? That's a full curve. What about 1 pi? That's not a full curve. Okay, so it's somewhere between 1 pi and 2 pi. What about 3 pi over 2? Right? Oop, except I didn't do it right. Not a full curve, and so on and so on and so on. So you can mess around with that. You can also, right, so that's kind of using technology and trial and error. You can also kind of copy what I'm doing. So let me turn off that curve. Because if I just graph the curve in general, it just graphs a curve. So I'm playing around with this a little bit because I wanted something that would work for all sorts of situations. So I actually put constants in. So I said a minus b cosine c theta. But the tricky part is that I said I want theta to be less than or equal to d, where d is this constant slider bar down here. And so then for this problem, and this part's just the point at the end of the curve, you don't technically need it, right? I'm just graphing that, right? That's x and that's y, right? It's r cosine theta, r, Here's r sine theta. That's all I'm doing right there. But you don't need that part if you don't want it. But then look what I did. I made a equal to 1, so that'll get me my 1, b equal to -2, and c equals 1, right? So that way, when I cycle through, I can actually watch the curve built, which is more fun than just playing around down there. So I can see, oh, look right there. It's happening right around 2 pi. So I can play with this. And the tricky part is, it's not tricky, it's this part right here. That's the beautiful part. You don't need the point. The point just gets you where the end of the curve is. I just like it because it's pretty. But you need this piece. So you need to say theta is less than or equal to d, right? So I could do that down right here. So I can turn off this graph. Let me just turn off the whole thing. And so then I say down here, forget it. I say r equals 1 plus 2 cosine theta, and I put in a curly braces, and I say theta is less than or equal to d. And then I say graph it, and it'll work, right? It doesn't have to be anything fancy. So 1 plus 2 cosine theta, theta less than or equal to d, and then when I cycle through my slider bar for d, I can see, oh, it's right there. It's 2 pi. 2 pi is my period. Right? Put in a fancy one here, and you're welcome to use it, because then you can kind of change it for any problem you might need that involves a plus or minus b cosine c theta. Right? But if you don't want to get that involved, you can actually just type the problem, but just put in the theta is less than or equal to d part, and then you can have a slider bar for d, and it'll let you cycle through it, and you can spot the period that way. Nice. It's a little bit easier, honestly, once you get used to it, than mucking around with the whole theta part down here. Okay, so we saw that this particular one has a period of 2 pi. Now this one doesn't have a period, and I can prove it to you, but let me go graph that graph, which is right here. And again, this one's not nearly as involved. I actually just graphed the graph, and I just put in that little bit, theta is less than or equal to d. This part you don't technically need. That's r cosine theta, r sine theta. I'm making a point because I like having a little point at the end of my graph, but it's not strictly necessary. But watch what happens as this graph gets built. So if I start with d, around and around and around it goes, and it's just getting bigger and bigger and bigger. There's infinitely many concentric loops, and it actually stops. Desmos doesn't really let us graph much past 12 pi, so it kind of quits on us, but we can see that this is going nowhere. Spirals and concentric loops like this, they're not periodic. So not periodic. Those spiral graphs we graphed a while ago, there was a spiral we graphed, actually 2 of them. They don't have a period either. They just keep spiraling, right? So there's infinitely many concentric, that's an N, concentric loops. And we'll make a big note. Spiral graphs also are not periodic. Right? There's no period for a spiral graph. It just keeps spiraling. Okay, now the next one's kind of a fun one. It's kind of a weird flower curve, right? So a rose curve that's actually starts looking like a rose in my opinion. So let me cycle through. So again, for 12c, you can see I'm just graphing it. I put in b sine of c theta, and I let c be 2/3, and I let b be 2. I'm just doing that because I want it to be able to be used by students for any kind of problem they want. So I'm going to go through. Right? So think about that. 2 pi did not have it. Look, there's 2 pi, and we're nowhere even close, right? So keep going, keep going, keep going. Whoop, right there. It happened. Kind of halfway between 0 and 12 pi. That's 6 pi. So it happens right around 6 pi, right? Actually, exactly at 6 pi, right? So that is the period for this one, 6 pi. Fun, huh? Okay, so that one's 6 pi, and let's see about d. I've got d right here. So d is right here, so let's go back down. So d goes through once, twice, and we're done. Right there, you're done. Everything else is just overlap. So that happens at pi, actually. So this one is 6 pi. And this one was just pi. So one more time, the trick is when you're in Desmos, just tell it that you want it to graph your function, right? B cosine k theta, but theta is less than or equal to d. If you add that bit in, I don't have to do the b and k. I mean, I can just put in 2 and 3, which was what it was for this problem. So this was 2, this was 3, right? 2 is right here, 3 is right here, right? They're slider bars for me. But it's fine, right? It'll work. But the key part is getting that theta less than or equal to d braces added, and then it'll add a slider bar for you right here. And then you can use that to kind of cycle through the graph. You don't need the point part, that little extra dot. I'm getting it by this piece, right? R cosine theta, R sine theta, right? Because this is R right here. So I'm putting that in and then multiplying it by cosine. But you don't have to have that piece if you don't want it. But you do need the function, and you need theta to be less than or equal to d. And then you can play with the slider bar and you can discover yourself what the period is. It's a little bit easier than trial and error once you get used to it in Desmos.